This is LeetCode 3403. Find the lexicographically largest string from the box. This is the daily problem for June 4th, 2025. So we're given a string word and an integer numFriends, and basically we need to split the word among the friends, and so non-empty strings. And so we're going to do that, all combinations of splits, and then we want to find the lexicographically largest string from all of those combinations. So so example one here, you have DBCA and two friends, so these are the possible splits, and right away you can recognize that this is basically very similar to stars and bars, right? So, if the string is D, that's kind of thick. Let's skip there. D, B, C, A, right? And then we can split. So in this case, K is 2, right? NumFriends is 2. So, if we have n elements in K groups, so we would do K minus 1 bar. So we could split it here, we could split it here, or we could split it here. And so in this case, if we split it here, we get DBC, and that's the largest lexicographic substring under those conditions. So right away, we can recognize that, sort of one of the first things I recognized is that there's a limit as to how long the string can be, right? So let's say we have a string like DBCA, B, right? So it's 5 letters, and then N is 3, right? The largest substring we can have is going to be length 3, right? Because we have to place 2 bars in this case, n minus 1. So we could do this, right? And then this would be the longest substring. That's important because every person has to receive at least one character. It's non-empty, right? So every person has to receive 1. So that means that the longest length string is going to be length of word minus n plus 1, right? Where n is the number of friends. So in this case, you have 5 characters, minus 3 is going to be 2 plus 1 is 3, so that's going to be the longest possible substring if we have to give each person at least 1 character. And very quickly, once I recognized this, I was like, okay, this is just sliding window, because all we need to do is just have a sliding window of this length and go left to right and just look at all the substrings. Now, the reason you're going to do that, right, is because of how lexicographic works. So essentially, if you were to brute force this, right, if you were to brute force like every single combination of these characters here, substrings here, you would check D, you would check DB, you would check DBC, and etc. You wouldn't check DBCA because that would exceed this length, so you wouldn't check that. But you would check, D, DB, etc. But the way lexicographic works is that if 2 strings are identical, right? So let's say we're comparing D and DB, right? D and DB. So you check index by index, right? So the first index is the same, but the second index, you have a character here, but you don't have a character here. So this string is automatically lexicographically larger because it has an extra character, and all the previous characters were the same. So that means that if we're looking for the lexicographically largest, why would we check just D or just DB when we could check DBC, right? So we don't actually have to check any strings less than this width. So essentially, it's just going to be a sliding window of this length going left to right. And the only nuance is that once, so you would first check this, then you would check this, then you would check this. And then here, when you want to check this, you kind of have to handle this case where, okay, now your window is outside the length of the string. So you just want to fix your right pointer at the end. And so you would check A, B, then you would check B, and then you'd be done, right? And then you'd keep track of whatever the longest, so you'd have some result variable keeping track of whatever the largest string you've seen so far is. So let's implement that now. So right off the bat, one of the edge cases is going to be if numFriends is 1. So that's an edge case because there's only one substring in that case, so you would just return the word friends equals 1. Otherwise, we're going to have our results, and we're going to initialize our pointers to be 0, and then the window size is going to be length of word minus numFriends plus 1, right? We've established that. And then we're going to say while L is less than length of word, because we want the left pointer to go all the way to the end, so eventually we want to end up here. We're going to say result equals max of word in that window, so L to R. And so we're just going to, this is just keeping track of the largest lexicographic word we've seen. And Python, when it does string comparisons, it compares them by lexicographic length. That's why we can use max here. And then we just, we'll increment our left pointer, and then we'll increment our right pointer, but we only want to increment our right pointer as long as it's not at the end, right? If it's at the end, we can't increment it, but if it's before the end, we can still increment it. So we want to say if R is less than length word, we can increment that. And at the end, we just return result. And yeah, that works. And it's pretty efficient. This is O of n time complexity because it's just a sliding window. So it really reduces the number of substrings you have to check, because otherwise, if you were doing this brute force, there'd be a lot of substrings to check. So yeah, that's this problem.